All right, welcome. So last day we talked about how to develop the moment generating function. Of course, that's going to be something that I will ask you to do, but as an appendix, and I'll grab it. I didn't grab it yet because I had to scroll all the way to the back of my textbook, but I'll post the appendix. And maybe I'll just show you. Can I, how can I go? I want to go to the very end. Anyways, at the back of your textbook, there's an appendix. Maybe I'll show you here. With all the moment generating functions for a lot of different distributions. So some of the common distributions, and so that table is going to look like this. I can't really see, but so it's going to have the PMF or the PDF, as well as the moment generating function. And so we need to know how to use that, right? And so I'll post that so that you have it, or some version of it, on our Moodle page. But just for some review, right, we said that to find the moment generating function, and that's all we got to, right? We haven't talked about, how are we going to use it? Why do we want to use it? Oh, I forgot to move my microphone closer. Can you hear me now? Okay. So we established how we found the moment generating function, and it's a special expectation. And so we said that the moment generating function, oops, make sure it says function is the expected value of e to the power of tx. Okay. So we usually denote that by m, capital M, or even a lowercase m, subscript x of t, which, depending on if we have a discrete or a continuous function, that's going to determine. So we might have to have an integral if we have a continuous function, or we have a summation if we have a discrete function. Okay? And so what's going to happen, and I'll just bump this over so it's kind of more front and center here, right? But this is what we established. It was assuming that, I can't remember how we said it exactly, but it couldn't be diverging, right? And so I'll leave that from last day, but for now, right, this is what we want to focus on, the moment generating function. We also said that the first moment is e to the power of x to the power of 1, which is just e to the x, or sorry, e of x, not e to the x. And then the second moment is the expected value of x squared. And just so it doesn't look like a prime, I'll make this a 1. It looks like a 2, doesn't it? Here, I'll go in and I'll go like that. Make sure it's a 1, right? So that's the expected value of x to the power of 1. And so that's just the expected value of x. The second moment is the expected value of x squared, and so on and so forth, right? And so we can find all these moments, and then we can generate different parameters from there. The mean, sigma squared, so the variance, And so we said that the variance is really just the difference between the second moment and the first moment squared. Okay, so we also said, let me see, how did we say it? That the variance of x is the expected value of x squared minus the expected value of x squared. Yeah. This is the second moment minus the first moment squared. Okay, and so we can use that, right? Especially if we have a moment generating function. You can imagine a moment generating function, so that's where we're going to pick up today, is a function that gives you the moments, right? So you can specify which moment you want, and then we can do a little bit of work, but not as much as if we had to integrate all over again, or take a summation, but usually we're integrating. And so the moment generating function is a function that we can use to generate moments. Seems weird, but notice that that's going to be useful if we can rephrase everything in terms of moments. Okay, so I'll kind of cap that as our review, and we'll say something like, so moment generating functions are used to generate moments, okay? And so that's how we use them, but they also have a lot of other properties that are going to be beneficial. There will be times, the variance of x is, sigma squared. Which is the x minus mu of x squared summation over n minus 1, or over n, because it's the sigma squared. But anyways, we're going to end up using this formula here. Okay. And so for the variance. Okay, so there will be situations where it might be easier to use the PDF and take the integral, for example, right? But usually it's going to be easier if we use the moment generating function. Okay. Because usually what we want is we want to find the mean and the variance of some distribution. Okay. And so moment generating functions, it's all coming back to me now because I ended here because it's a nice kind of starting summary, I guess. So moment generating functions MGFs, there are a lot of acronyms, right? We started and we talked about the PMF, that's for a discrete function. Then we talked about the PDF, that's for a continuous function. Then we talked about the CDF, which is the cumulative distribution function, right? And that applies to either continuous or discrete functions, right? So that's the cumulative distribution function. And now we're talking about MGFs, right? So it might be useful to have a little kind of quick reference summary. The more you talk about them, the more they'll start to make sense, and you can kind of just use the acronyms. But I know in the beginning it's hard to keep track of the PMF, the PDF, the CDF, the MGF, LN and F, right? And so, but just we'll get used to saying them and using them. Okay, so the moment generating function, the MGF, can be used to generate moments, which is what we'll usually do. But they turn out to have but they turn out to have lots of other useful properties, which we will learn about. As the semester goes on. Right, so as we progress, we might come back to, or we will come back to the MGF, and we're going to talk about it some more, and we're going to develop it some more. Okay, and so the reason we like the MGF is because it's easier to learn about a distribution using the MGF, the moment generating function, than it is about the PDF or the PMF. Okay, so it is often easier to learn about a random variable via its MGF than to work with the PDF, PMF, or CDF directly. The PDF, just as a reminder, that's for a continuous function. PMF, that's for a discrete function. Or CDF directly. Of course, the CDF is the cumulative distribution function. So up until what point, what's the probability of being less than or including that point? That's the CDF, and that applies to both distributions. Okay. So let's have a look at an example of building an MGF. Now, like I said, this is something that you should be able to do, but at the end of the day, the MGF, I'll give you a table with all the usual MGFs, right? But it is something that we need to be able to develop. Okay? And so, as an example of finding the MGF, of finding an MGF, consider a uniformly distributed random variable. Consider a uniformly distributed RV, random variable, with PDF. Okay, so the uniform distribution, we're assuming we have a continuous uniform distribution, and so the PDF is going to be f of x is going to be 1 over b minus a for x between a and b and 0 otherwise. Okay. So that's a uniform distribution between any points a and b. And so then, of course, the total area has to be 1, and then we take it and divide it by the length to get the height, which is the probability function f of x. So to find the MGF of this continuous function, right? Because notice here we have this continuous function, so we have to take the integral, right? And so its MGF is I'm going to drop the subscript x here, m of t, because it's obvious that x is going to be the variable. But you could keep it on there if you want. In general, it's from negative infinity to positive infinity, e to the power of tx times f of x dx. This is true in general. Okay, so that's the definition of the MGF of a continuous random variable. Okay, so for us, right, so in this case, the moment generating function m of t is going to be restricted to the integral from a to b of e to the tx times 1 over b minus a is f of x, right? And so I have times 1 over b minus a with respect to x. 1 over b minus a is a constant, so I can bump it outside of the integral with wild abandon, right? And so here I have 1 over b minus a times the integral from a to b of e to the tx dx. Now, it's going to be really, really useful to remember that the integral of e to the tx is e to the tx over t, okay? And so here, right, because we're going to integrate this often, right, because it's part of the moment generating function. So as soon as you have a continuous random variable, you're going to need to do some integration on e to the tx, right? And so the integral of e to the tx dx is e to the tx over t. Okay, that's going to be really useful to just remember, right? You could look it up. You could even use, some online calculator to confirm your integrals and even your derivatives as we get to them, right? If they're feeling kind of rusty or if you're not feeling up to snuff, then that's totally fine. I'm not here to test your calculus skills, but we are going to use them, right? So as long as you're able to find, the integral that we need or the derivative that we need, if that is with an online calculator, that's fine by me. I'm sure that if you're in the data science program, right, some other profs might expect you to do it kind of in your head or whatever. So just be aware of that. But for me, no, we're focusing on just what we need to do, right? We have to integrate this because we need the area under the curve, for example, right? Or because we're trying to find this moment generating function, which by definition is an expected value, which is an integral, right? And so let's see here. So then when I integrate this, what do I get? Well, I get 1 over b minus a, and then times e to the tx over t from a to b. Okay. So I let x be b, and then I let x be a, and then I subtract those two. And so I end up with something like, and this is just a fraction times a fraction, right? I'm allowed to merge those. I just didn't want to jump the gun too fast here, but I end up with e to the power of tb over b minus a times t minus e to the power of ta over b minus a times t. Here I have a common denominator, so I'm allowed to subtract these two fractions and put them over that common denominator. So this is going to end up looking like e to the tb minus e to the ta. And it might be nice to write bt and at instead, but it doesn't matter. Over b minus a to the power, times t. If we think about this as a function, right, this is the moment generating function. One problem is, as soon as we have a fraction, right, we need to remember that we can't have 0 in the denominator. We can't divide by 0 because it's undefined, right? And so we need to consider that special case of, okay, if I have a scenario where I'm dividing by 0, I need to consider that separately. Okay, so in this case, if t equals 0, then we have a problem, right? Can b minus a be 0? No, right? In fact, it's always going to be positive because x is between a and b. So, but it's not including a and not including b, right? And so that means that just by is it the transient property or something like that, where if a is less than x is less than b, well, then a must be less than b. Can't remember what property it's called, but that's what it is, right? So then a must be strictly less than b, which means b is always going to be bigger. So b minus a is always going to be positive. Okay, so here, this b minus a will always be positive since a is less than x is less than b. Okay. For the moment generating function to exist, so m of t does not exist, and I was going to do d and e, but maybe I should write it out, does not exist at t equal to 0, right? Because we can't divide by 0. Since we can't divide by 0. Yeah. So, but what we can do is we can look at the limit as t goes to 0. Oh, limits. I thought we were done with limits. Never done with limits. Ugh. But we can get away with not considering limits so often, right? But so if we think about, because there are no restrictions, right? Sorry, I just had to check. If I had a log up here, for example, then of course I can't take the log of a negative number, but I have no restrictions on any of the inputs here. So I'm okay in the numerator. It's just I need to consider this t in the denominator. What's going to happen is that this t is kind of always going to be there, right? Because we're integrating e to the tx becomes e to the tx over t, right? So there's always going to be some version of this t in the denominator, okay, or usually. Okay, so here, what we're going to say is that note that m of t only makes sense for t not equal to 0. Okay. But we can show using L'Hopital's rule, remember L'Hopital's rule? We throw it in at the very end of Calc 1 and we say, oh, it's too easy to find limits this way. You're not allowed to use it all the time, but we have to use derivatives, right? But it makes it a lot easier. And so it helps us out if we end up dividing by 0 or something like that. Then we can use L'Hopital's rule. L'Hopital's rule, or sometimes we write L'Hopital's. So you can have the S or you can have the little, I can't remember what this accent is called, but so L'Hopital's or L'Hopital's rule, they're the same. That the limit as t goes to 0, right? And so here, this is from this t can't be 0, right? So now we take the limit as t goes to 0 of this function e to the tb minus e to the ta over b minus a times t. I'm running out of room on this page, but I'm going to try to keep it here. Is the limit as t goes to 0 of, what can I do? I can take the derivative, right, with respect to t, both the numerator and the denominator, and I can rearrange them as a fraction. And how do we usually write it? We usually write LH here over the equal sign to show that I'm taking the derivative of the numerator and the denominator separately, right? So you don't need the quotient rule or anything. You can just do it separately. So that becomes b e to the tb, right? Chain rule, minus a e to the ta over b minus a, which is a constant, times t, but the derivative with respect to t is b minus a. If I let t goes to 0, right, I have e to the power of 0, right? And so that's the benefit of using L'Hopital's rule, is now I can kind of direct substitution here. T equals 0, I get b times 1 minus a times 1. So that's b minus a over b minus a. That just puts me at 1, right? So here, 1. And I didn't write out that step because I wanted to keep it on the same page here. I know. But hopefully that made sense. Okay. Because as we take the limit as t goes to 0 here, e to the tb and e to the ta both go to 1. Okay, so the MGF then is going to have two different definitions. So again, it's going to be a piecewise function depending on if t is equal to 0 or if it's not equal to 0. So the MGF is m of t is e to the tb minus e to the ta over b minus a times t, right? And that's if t is not equal to 0. And if it's 1, if t equals 0. Okay. So this is the moment generating function. How can we use it? We use the moment generating function by taking the derivative of the moment generating function. What a mess, right? No wonder you have to have Calc 1 and Calc 2 to ride this ride, right? And so, first, right, we integrated to find the moment generating function, And then now we're going to take the derivative to find the actual moments. In fact, we take the derivative and evaluate it at 0 to find the different moments. So we use m of t to find various moments by differentiating which one. Of course, we're not going to differentiate the constant 1. We're going to differentiate this portion, the t not equal to 0 portion. So by differentiating the t not equal to 0 expression, and using L'Hopital's rule again, to take the limit as t equals 0. Sorry. I skipped ahead. No, I'm not going to say that. I skipped ahead and I had another note that I wanted to write out, but it's okay because I think we already talked about it. So we use the moment generating function m of t to find the various moments by differentiating the t not equal to 0 expression. So in general, if m, so lowercase m is a positive integer, and if we define that m and then in brackets m of t means the mth derivative, of m of t, we have by repeated differentiation with respect to t. So we have by repeated differentiation with respect to, hopefully you guys are okay with the WRT with respect to, I'll define it once, but hopefully you've seen it before, WRT with respect to t. So then we find that the mth derivative of m of t evaluated at 0 is the expected value of x to the power of m. Remember, e of x is the first moment, which means we take the first derivative of the moment generating function and evaluate it at 0 to find the expected value of x. The variance uses the second moment as well as the first moment, but if we want the second moment, e to the expected value of x squared, well, then we're going to have to take the second derivative of the moment generating function and evaluate it at 0. Okay. So here, right, the expected value of x, which is mu, and maybe I'll do this, I'll write mu on the other side here. So mu is the expected value of x, which is m prime at 0. Sigma squared is the variance of x, which is the expected value of x squared minus the expected value of x then squared. Right, careful with those two squares. One's on the x and one's on the e of x, which is the second derivative of the moment generating function minus the first evaluated at 0 minus the first moment squared. And just to emphasize that that square is on the outside, I'm just going to wrap up that first moment evaluated, or the derivative of the moment generating function at 0. I'm going to wrap it up in a square. So notice, right, we can find a lot of information just taking the derivative of the moment generating function and evaluating it at 0. Okay. Here, right, you could make use of something like Maple, right, where you can make Maple calculate the fourth derivative, right? We don't have to do it by hand, but we need to know that that's what we need to do, right? And so I've got an example, and it's using a discrete function, because I often tend to just focus on the continuous functions, but sums can be tricky too. So I wanted to do a discrete function. So as an example of a discrete random variable, consider the PMF. Maybe I should kind of highlight that it's an example. Consider the PMF for the number of heads, on 3 coin flips. So P of X is 1 in 8 if X is 0. And maybe I don't have to write that if. I'll just have X equals 0 beside it. It's going to be 3 in 8 if X is 1, 3 in 8 if X is 2, 1 in 8 if X is 3, and keep it on the same page, 0 otherwise. Oh, come on. So we've got this piecewise defined function, and that's always going to be the case for a discrete random variable. Okay. So if we have to find the moment generating function, what do we have to do? Really what we're finding is the expected value of e to the tx, right? Which means that we have to take the sum in this case, because it's a discrete random variable, of e to the tx times p of x, right? Over all the possible values of x. So it's MGF is what? It's going to be M of t is the sum from x equals 0 to x equals 3 of e to the tx times p of x. So if I think about e to the tx, well, I could have x equals 0, x equals 1, x equals 2, x equals 3. Those are all my options, right? And of course, if we had a bigger summation, you don't want to do this by hand, right? You want to kind of find a way to do it, but you might have to do it by hand. Depends on the situation, right? But usually it's going to be something kind of quick like this, right? With only basically 4 summations. So we have e to the t times 0, right? Starting at x equals 0, and p of x when x is 0 is 1 over 8, right? So times 1 over 8 plus e to the t of 1 times, well, if x is 1, p of x is 3, or p of 1 is 3 over 8. plus if x is 2, t times 2, e to the power of t times 2 times, whoops, p of 2 times p of 2, which is also 3/8, plus, and then finally, let's see if I can, e to the t times 3 times 1/8. Well, the other ones would be times 0, so they don't matter, and that's fine. Okay, so looks like I have a common denominator of 8. So I'm just going to squish these all together right away. And I'm going to show that this becomes e to the t times 0. E to the 0 is 1, right? So 1/8. So 1 plus 3e to the t plus 3e to the 2t. I'm going to rewrite that as 2t. A little bit cleaner with the coefficient in front. Plus e to the 3t. And then that's all over 8 because that's the common denominator. Now, here, I'm going to make the leap. I'm going to factor this and I'm going to show you what it is and you can confirm what it is. But to me, unless you have these kind of third expansions memorized, which I don't really expect you to do, right? But it might be nice to recognize that if you have 1 and then 3 and then 3 and then a coefficient of 1 again, then what happens is this becomes, and I just want to show that it's not obvious, but it makes it easier to work with if we rewrite it as 1 plus e to the t to the power of 3 and then over 8. Okay. So this, you don't need to rewrite it like this, right? So factoring it and figuring out how to do it, it's quite a bit of work, I get it. But you can rewrite this, right? You can expand it and convince yourself that it becomes what we need it to be, right? And so here, this is where I would probably rely on, Maple or I haven't really used Wolfram Alpha that much, but I'm sure they would do it for you, right? And so you just need to convince yourself that these are the same, and we could. So here's where I want you to not worry so much about this if this wasn't obvious, right? We definitely could do all our future calculations with this expanded version. There's nothing wrong with that. They're the same, right? But it's easier. So here, we could use the first version in our calculations, but the second will be easier. Right. And so I only mention that so that you don't feel this panic of, oh, that wasn't obvious to me. It's not obvious. Right. But you can use software and it'll help you kind of get there. Okay. So what if I rewrite this as 8? I can rewrite as 2 to the power of 3 so that I have everything to the power of 3. So this becomes 1 plus e to the t over 2 to the power of 3. Right? Noticing that I pulled that exponent outside to make it even easier to deal with. Yeah. So what did we find? We just found m of t. Now, if I have to find the first moment, that means I have to take the first derivative of this and then evaluate it at t equals 0. Okay. So to find the first moment, we need to find m prime at 0. Okay. Which means that first I need to find the first derivative of m of t. So m prime of t is going to be what? So this is m of t, and I'll remind us down here, just so I don't have to scroll up and down so much. I'm going to need to use the chain rule here, right? The derivative of the outside, so bring that 3 out front and then decrease the power to 2 times the derivative of the inside, right? I only have a t in the numerator, so luckily I don't have to use the quotient rule here because the t is just in the numerator. So what I end up with is I get 3 times 1 plus e to the t over 2 to the power of 2 times the derivative of the inside, which is, I can bring that 1 over 2 outside the brackets, and then I have 0 plus, remember the derivative of e to the t is just e to the t. Oops. Okay. This is from the chain rule. Okay. Derivative of the outside times the derivative of the inside, which puts me at, okay, I can shift this 1 over 2 because I'm just multiplying through 1 over 2, and then 0 plus e to the t is just e to the t times this 1 plus e to the t over 2 all squared. So I get 3 over 2 times e to the t times 1 plus e to the t over 2 squared. Yeah. That's going to be the first moment, okay, if we evaluate it at 0. So now, right, we find that the first moment is m prime at 0, which is going to be 3 over 2 times e to the 0, which is 1, right? Times 1 plus e to the 0 over 2 squared. Right, remembering that e to the 0 is 1. So then I get 3 over 2 times 1 times 2 over 2, which is 1. 1 squared, still 1. So I get 3 over 2. And I've got a page break here, so I'm just going to keep it like that. Okay, so what does that mean? That means that I have an expected value of 3 over 2, right? So here, this becomes, and maybe I'll use this color here, which is the expected value of x, which is mu. What if I have to find the second moment? Remember, if I wanted to find the variance, the first step in finding the variance is to find the second moment. To find the variance, we need to find the second moment, which is, by definition, it's the second derivative, right, of the moment generating function evaluated at 0. So first thing I'm going to do is I'm going to find the second derivative. So m double prime of t. Now remember, that's going to be the derivative of this, right, of the first derivative. So now we just keep taking the derivative, and it's going to get nastier and nastier, right? But it works. So here, let me just copy this. M prime of t is this. I basically have a function times a function, right? So here, this is the product rule. And the chain rule is built in, right? One of the functions is a chain function. And so if I let this be f and I don't know, this be g, then the derivative is the derivative of the first times the second plus the derivative, the first times the derivative of the second. So remember, the product rule says that the derivative of f times g is f prime g plus f g prime, right? You can switch those around if you want to, but I always think of the derivative of the first times the second plus the first times the derivative of the second. Okay? So if we take it nice and slow here, we can get to the second derivative pretty quickly here. So if I think of 3/2 times e to the t, that's an easy derivative, right? Because e to the t is the derivative of e to the t is e to the t. That's the beauty of it. Times a constant, well, nothing changes. So I have 3/2 e to the t times the second, which is just going to be 1 plus e to the t over 2 all squared. Okay. And maybe I'll need to give myself more room here because I need to use the chain rule on the second one. So now, if I look back here, so next thing I have to do is I have to just hold the first function steady. So that's going to be 3/2 e to the t. Okay. And then times the derivative of the second. Now the derivative of the second requires another chain rule, right? And so the derivative of the second is 2 times the derivative, or times the inside, 2 times e, 1 plus e to the t over 2 to the power of 1 times the derivative of the inside. I can pull out that 1/2 times 0 plus e to the t. So I just want to highlight where everything went here, right? This is f prime. This is f. This is g. And this is g prime. Okay. Just in case, because it might have been a while since you used the product rule, right? And so doesn't hurt. And I always find that if I go nice and slowly and I pick through it, it makes a little bit more sense. Okay, so now I can simplify this, right? I can simplify, I've got 2 divided by 2 because this is all being multiplied, right? So I can cancel some of these 2's. I still have an over 2 here, but I also have 0 plus e to the t is just e to the t times e to the t. That gives me e to the 2t, right? So I can kind of consolidate, massage this a little bit. And what I get is I get 3/2 e to the t. So the first chunk doesn't really change much, or it doesn't change at all. 1 plus e to the t over 2 squared plus 3/2, because here, maybe what color can I use? maybe I'll use this kind of yellow. All right, those two cancel. And so plus 3 over 2 e to the 2t times, because now I've taken care of all of this over here, right? But then I have to have times 1 plus e to the t over 2. No power anymore because it's a power of 1. Okay. So now the second moment is going to be what? And I'm going to try to show it. Okay. So then the second moment evaluated at t equals 0, it's going to be 3 over 2 e to the 0 times 1 plus e to the 0 over 2 squared plus 3 over 2 e to the 2 times 0 is still going to be 1 times 1 plus e to the 0 over 2. A lot of this kind of goes to 1, right? All the e's go to 1. And then we have, so I'm just going to take some time here, 3 over 2 times 1 plus, and maybe I'll just write 2 here, 2 over 2 squared plus 3 over 2 times 1 times 2 over 2. 2 over 2 is 1, 1 squared is 1, so I get 3 over 2 plus 3 over 2. Womp womp. All right. Putting me at 3 plus 3 over 2, which is 6 over 2, which is 3. Okay. Which is the expected value of x squared. So now we can find what the variance of x is. Okay. So now we can find the variance. Sigma squared is the expected value of x squared minus the expected value of x then squared, right? Or if you prefer, or the expected value of x squared minus mu squared. You can write e of x or you can write mu, and we can use them interchangeably, right? So depending on what you prefer to see, you might be replacing them with mu or just keeping them as e of x. I like to keep them as e of x, but that's just me. Which is the m double prime at 0 minus the m prime at 0 squared. Which in our case, we found both of these values. The expected value of x squared, or the second moment at 0, is 3. So 3 minus, and we said the expected value of x, or the first moment at 0, is 3 over 2. So 3 minus 3 over 2 squared, right? Careful when you square that, right? It becomes 9 over 4. So 3, I can put it over a common denominator. So I get 12 minus 9 all over 4, which is 3 over 4. Nice. Okay. So a lot of stuff going on, right, with this moment generating function. You can see how it would be useful, right, as long as we have something that's relatively easy to differentiate, right? Then we can kind of rattle off a lot of these expectations, right? And from the expectations, we can find the variance and of course the mean, because it is the expected value of X. So let's just go backtrack here, right? We started with a discrete function, right? Which means we had to take the sum. This could have been an f of X, so a PDF for a continuous random function, but the idea is the same. We integrate over e to the t of X or e to the tx times f of X dx, right? And then we would be able to find that moment generating function. And then we take the derivative of it first time, second time, potentially third time, fourth time, whatever, and evaluate them at 0, and then we can use those, right? So once you have that moment generating function, then it becomes a lot easier to find things like mu and sigma squared, right? The mean and the variance. Okay. The last thing we're going to talk about in this chapter, can't believe it, we're finally finishing chapter 1, are some of these important inequalities. Now, they're important, but I'll bring them up as we need them, right? There are just a few that I want to introduce, and I'm not going to go too deep into them, so we're not going to go through the proof or anything because it's in the textbook. And I just want us to see them, right? And so there's one with a quick example that I want to use if I get there. We'll see. Okay. Oh, and I'd love, well, I guess there's only 3 of you here, but for the lab tomorrow, do you guys like it when I pre-record and you guys just work through it, or would you prefer to meet at the scheduled time? Sometimes it depends on the material. I might prefer to pre-record it so that you all hear the same thing. And then sometimes I might want to meet with you guys, but I'd love to know what you like it pre-recorded. That's what I thought. I just kind of assumed that that's okay, good. Just to have an idea. Yeah, because sometimes it's like, yeah, 3 different options. So you like pre-recording, whatever you like, and if it's easy, then it's fine. Okay, got it. But no, that's good. So because I'm having a hard time kind of getting a read on what people like. I'm thinking if I was a student, I probably would like the pre-recorded, but then I don't know if I would actually do it because I'm a procrastinator. But so anyways, what I might do is whatever we don't finish here, I've only got a couple of pages that I want to get through. So I'll post it as part of the lab recording for tomorrow. And then we'll just have a recording for tomorrow's lab. Seems good. Especially when I'm talking about, yeah, I'm like, okay, the people have spoken. I'm going to do what they sort of want. It's what everyone sort of wanted, a recording. Or said they were okay with. Yeah, that's a lot of trust in my abilities. We'll see. So whatever we don't, oh yeah, so now that we're chatting, I was thinking about the test too, and I might take us into chapter 2 just a little bit, because we basically do everything all over again, but with joint probability distributions. But I also feel like it's time for a test. So we might just have a test on chapter 1. That might be good, but I'll give you guys some practice problems before that. So I still, I'm behind where I wanted to be, obviously, and then we'll see what we can do. Yeah, you need some practice problems, I know. So I'll post that as well. I know, so many formulas, so much theory. And what are we supposed to do? The only thing is from today, right? Find the moment generating function, use it to find the expected value of X and the variance of X, right? That's like really the first applied thing we've learned. So good for today. Okay, but we need practice with it. Oh yeah, so the last section, that's what got me started. Can you believe it? It took us this long to get through chapter 1. There's so much stuff and I cut so much. 1.10 is just on some important inequalities. Okay. I know. Yeah, some of those areas, there's some stuff that we don't have to worry about, right? So I'll steer you in the direction of what's going to be important. So definitely being able, so from today, definitely being able to find the moment generating function and using it to find the expected value of X and the variance of X, that's going to be a pretty big deal, right? And so we can focus there, right? We had to build up on, okay, how do we, how can we use these things? What are some other ways we can do it? But yeah, the main applied thing that I can think of is what we just covered, right? So I'll give you guys some practice problems there. And then you're still going to feel lost. That's just how it is with this stuff. Okay, so there are some, I'm going to focus on 4 important inequalities that we're going to use. And so I'm just going to introduce them here. We're not going to do the proofs or anything. The proofs are in the textbook, but we just want to have them as tools, okay? There are some important inequalities. We will use throughout the course. Okay. We will state them here, and the proofs are in the textbook. Okay. But don't worry about the proofs. One thing that I will say is you should be able to read the proof and kind of convince yourself that, okay, yeah, that makes sense. But it's not I'm not going to make you memorize proofs or anything or do any rigorous proofs, right? I might get you to do mini proofs, but I'll set you up and I'll warn you if that happens. So we will state them here. You can find the proofs in the textbook. Okay. So in general, we're going to be talking about the relationship between expected values. Okay, so in each case, there is an inequality relating to expectation values. Relating to expectation values. Oops. The expected value of G1 of X is going to be greater than the expected value of G2 of X, assuming that G1 is greater than G2, right? So since the expected value of G of X is the integral from negative infinity to infinity of G of X, F of X, dx. And what's going on here? Well, F of X, F of X is greater than or equal to 0. Why is that? Because it's a probability distribution function, right? And probabilities have to be between 0 and 1. And so it definitely has to be greater than 0. All right, probabilities have to be greater than or equal to 0. So then, if G1 of X is greater than or equal to G2 of X, remember if you have two functions that at one point X, right, you can look at the output of G1 versus G2 or G1 versus G2, and you can figure out which one is larger, right, in the Y value. So this just means that G1 of X is above G2 of X. Okay. Over the range of X values. Don't get too hung up on the range. The range we usually use for the Y values. But in this case, we're talking about all the possible X values, right? But context tells us that. And so over the range of X values with F of X greater than 0 implies that the expected value of G1 of X is greater than or equal to the expected value of G2 of X. And that's just because G1 is larger than G2, right? So then the expected value, if we think about, let's see if I can pull this off. If we call, this function G1 of X, and we call maybe this function G2 of X, remember that the expected value is the average, right? And so it's going to be the average output, okay? And so the average of G1 of X, it might be here somewhere, right? And if we look at the average on here, well, maybe it's here. So we can see that this value is larger than this value, right? And that's because the function is just hanging out a little bit higher. So, okay, so we're going to build on that. And I think what I'll do then is I'll include it as, so I'll talk about just 4 of the main inequalities that we're going to use in the recording for the lab, and then we'll do a quick lab on expectations, okay? Expectation values, I should say. Okay, so that sounds good. I know I have 3 minutes, but it makes more sense to keep them all in one video. So I'll end it there, and I'll post on Moodle that we're gonna do the video thing again for the labs, because it gets confusing for me. So this way I say the same thing to all of you. And if you have any questions, let me know. Otherwise, I'll see you next week. And I'll stop this.